Hello and welcome to the module number 4 in the CS 4010, the finite element analysis and the structural dynamics. In these lectures, we are going to study the essence of the finite element method. Please note that not all of the pictures and the animations in these lectures are created by me. Some are inherited from the previous lecturer, and some others I just searched online with the label for reuse. So the subject learning outcome for our lectures is we should grasp the essence of finite element method. And in the tutorial, we are going to make a 2D finite element method application. The main idea of finite element method is we are going to divide a complicated shape into some standard elements with a known shape function. For example, I have an exact solution here, which is a circle. I can draw it with a compass. However, compass is not easy to handle, and circle is just only a simple shape. And I want to draw it with the rulers. So I want to simplify the circle, the curve, into lines. And if I draw only 4 lines, I will have a diamond, which is an unacceptable solution. If I increase the number of lines, I can have an octagon, which is an inadequate solution. And if I keep increasing the number of lines, I can have a approximate solutions, which is close to the exact solution. So the first conclusion you can conclude here is that the finite element methods don't give you the exact solution. It never gives you an exact solution, just an approximate solution only. And it is acceptable because in real life, we rarely have an exact solution because there are many other factors that can influence your solution. And for 2D and 3D, we can divide surface or volume into smaller elements, and we call this the tessellations. Delaunay tessellation is a very popular tessellation because it is unique. There is only one Delaunay tessellation for one set of points. If you draw a circumference circle for any triangle, you will notice that there are only 3 points in the circle and no other point will be included. So this makes the Delaunay tessellation unique. Apart from the irregular tessellation, you may have the regular tessellations like a square net. And now we are familiar with 2 very important concepts. The first one is a node, which is the vertices of the elements. And the second one is the elements, which are the volume or area that's limited by the nodes and the edges. 3 points to remind here. Firstly, displacement vectors only for every node in the mesh. That means we don't have displacement vector for element. We assume that we are going to calculate for nodes only, and all other will be interpolated or extrapolated later. Secondly, the finite number of unknowns that are required to be calculated, that will be the displacement, the force, and some other property at the nodes. And thirdly, the equation for regular element shapes and geometries are known and easy computed. There are 6 steps for the modeling preparations. In the first step, we have to do the symmetry reductions. That means if your structure is symmetric, you can just cut off the symmetric part and replace the interactions by some roller support or something like that. Or if it's uniform by one side, you can cut off the dimensions. Secondly, after the symmetry reduction, you need to choose the model type So it can be 1D, 2D, 3D shell, or 3D solid. And after select the model type, you have to think about the resolution of geometry. That means some detail may be omitted and it will not influence on your solutions. In the step number 4, you have to choose the element type and order for the elements. In step number 5, you have to think about the mesh density. That means you have to determine the appropriate mesh resolution. And in the final step of preparation, you have to approximate the loading conditions. As I told you in the previous slide, that in finite element method, we assume that the load is acting at the nodes, not on the edge or the volume or the area of elements. So the second conclusion is the central considerations is what element type is most appropriate. You can use this in 1D, you can use line. In 2D, you can use solid plane. In 3D, you can use 3D shell or a general 3D solid. The selections of element type will decide how accurate you are and how long the computation will be. Here is a landslide simulation by Parageotechnia. It uses 2D elements, the planes. And here is 3D cell simulations of the Ghent University when you try to simulate the buckling of a can. And for a general simulation, you may use a 3D solid element. Now we try to analyze 5 over 6 steps of preparations. In the first step, the symmetry is used to reduce the computational cost. For example, if you have a symmetric tempo like this, you can just cut it by half and simulate the reactions, the interactions between two parts by the roller support. Or the same thing to a bridge over a river. It's interesting that I make the bridge upside down. That means the downside is actually the sky and the upside is the river. Or you also cut by half for the plane hanger. Apart from the symmetric one, we sometimes has another type of symmetry is a periodic structure, like this lotus temple in India. So instead of simulation the whole structure, we can cut only one segment and replace the interactions with other segments by the roller support at the intersections. Here is another example of a periodic structure is a F&F tower in Panama. Because of the big enchants, so most of the structure are just symmetric but not periodic. So after the selection of dimensions of the simulation, we move into the resolutions of geometry. You know that the finite element method is an approximate method. Therefore, it will give you only approximate solution. Some details just add up the burden of the computations, and it doesn't influence your results. So here is an example of simplification from a complicated house into a very simple shape. And here is another simplification of the foundations and the influence from the structure. So the third conclusion you can note here is that it may be sometimes risky for the assumptions for the resolution of geometry, because when you study the behavior of structure, you often omit the foundation or assume that it is homogeneous. And when you study the foundation, you often think that the load from the structure is uniform. It is risky, but at the current moment, it is acceptable in engineering because we cannot simulate too much elements at the same time. Maybe in the future, with a new type of computers, we can overcome this obstacle. Here is another example of simplification. So a complicated building can be simplified to a flat building. In the fourth step, when we try to select the type of elements, it actually related to the step number 2 about the dimensions of simulations. So in 1D, you can have the light element. In 2D, you can have plane, which may be rectangle or triangle. In 3D, you can have it as a tetrahedron or a prism. So in terms of the triangle, we can have triangular or tetrahedral elements, or maybe wedge. In terms of a square, you can have quadrilateral or hexahedral elements. So in terms of the node, you may have the linear elements when we have the node only at the vertices of the elements. Or you can have the quadratic elements where you can have the mid-side nodes. Please remember that the mid-side node is computational expensive, but it can represent the curve geometry with fewer elements. In the fifth step, we need to consider the mesh density. Sometimes we do not really know if the coarse mesh is better than the fine mesh or not. The coarse mesh will save up a lot of computational time, but it sometimes makes typical error because the mesh is too coarse, so therefore it cannot simulate the tiny reactions or deformation. And sometimes the fine mesh is more than enough. We don't need that detail, and the fine mesh just adds to the burden of the computation only. Here is a graph of the computation cost, and here is accuracy level. You can see that at some point the accuracy will not increase because we reach the limit. The finite element method only gives the approximate solution, so therefore it's no point to go over the limit. And please remember that the accuracy of your simulation must meet the acceptable accuracy. You must remember the fourth conclusion that if the accuracy does not meet the acceptable level, there is no point to do the simulation. In the last step about the load simplification, we try to study the static and dynamics loads, and we have to simplify it into the nodal force. Please remember that in an original finite element method, we don't have the force act on the edge or area. We have the force act on the nodes only. So therefore, we have to simplify it to be an equivalent force. The governing equations for finite element method in static is Ku equal to F, and you may know it with the Hooke's law that F equal to Kx. In the dynamic, it will be Ku plus m second derivative of u by time equal to F by time. And in the model, you have the K, the stiffness matrix, times by the shape mode vector minus omega squared times by m times by shape mode vectors equal to 0 for the free vibration. The equation of statics comes from the Hooke's law, where we have F equal to Kx. And we have the strain epsilon equal to the derivative of u by x, where u is the displacement. And our stress sigma equal to E times by epsilon. In general, we have the vector of strain epsilon equal to the derivative of u by x, where u is a vector of displacement and x is a vector of positions. And sigma, the vector sigma, equal to the elastic matrix times by the strain tensor. In dynamics, we have the typical equations Ku plus m second derivative of u over dt square equal to ft. And please remember that for the explicit analysis, that's in the tutorial number 9, time step much smaller some value, so the simulation can be convergent. And for the implicit analysis, you can use Cranny concern, the central time, central space, or other methods. Now we move to the second part of this lecture about the shape functions. So for 1D, we know that the epsilon equal to du over dx, where u is a displacement and ui is a nodal displacement. They are not equal, but we try to calculate the displacement by the nodal displacement, which is calculated easily by the shape functions. So here is a scheme how we calculate the u and what is the relationship between u and x. We assume that there is a linear interpolation, so therefore we can have ux equal to n1 times by u1 plus n2 times by u2, and it will equal to the matrix of n times by the vector of u. Similarly, we have x equal to n times by vector x, where x is the positions and the vector x is the nodal positions. And now we check it for linear weighting function. If x equal to 0, I have n1 equal to 1 minus x on L and n2 equal to x on L. The solution works for all points along from x1 to x2. And for easy use, when the x1 is not equal to 0, I use a local coordinate zeta, where zeta comes from -1 to 1, for x comes from x1 to x2. And this way, I have n1 equal to 1 minus zeta over 2, and n2 equal to 1 plus zeta over 2 for any x. And I can check it with any positions of zeta, the local coordinate. In conclusion, we have ux equal to the matrix n times by the vector u, and the position x equal to the matrix n times by the nodal vector x. And this way, we submit into the epsilon calculation, the strain calculations, and we have epsilon equal to d zeta over dx times by the derivative of n by zeta times by the nodal vectors of displacement. And if I set b equal to d zeta over dx and dn over d zeta, I can have epsilon equal to matrix b times by the vector of displacement u, where u is a nodal displacement u1 and u2. And because we have n1 equal to 1 minus zeta over 2 and n2 equal to 1 plus zeta over 2, so therefore I have the dn over d zeta equal to -1/2 plus 1/2, and times by x1 x2 I will have the position x. And then I submit it into the epsilon calculation. I can have it equal to u2 minus u1 over L. So that is correct. Please note that the Jacobian matrix in 1D, we call it as the matrix of dx over d zeta. In the 2D simulations, we have two local coordinates, zeta and eta, which come from -1 to 1. And the value of n1, n2, n3, n4 for the node number 1, 2, 3, 4 is as shown on the slide. And when we try to convert the value from the local coordinate where we calculated with the standard solutions, we have to use the position vector xy equal to the matrix n times by the position vector x, where x is the nodal positions x1, y1, x2, y2, x3, y3, x4, y4. And about the displacement, we use the displacement vector E equal to uv, and it equal to matrix N times by the displacement vector of nodes U, and it's a nodal displacement vector. And this way we submit into the epsilon, and we have epsilon equal to matrix A times by E, vector E, where vector E is uv, where matrix A is the derivatives of the linear displacement by x, by y, and by tangent directions. And if we times the matrix A by matrix N, we will get matrix B and have the same solution like we did before for 1D solutions, for 1D simulation. That the strain tensor epsilon equal to matrix B times by the vector of displacement U. Please remember that the matrix B is the matrix of dimensions 3 times by 8, and therefore we have a lot of zero elements inside this one. It's not easy for computation, so therefore we should remove the zero element to have a compacted matrix. This one will be easier. We can calculate by the derivatives of the n matrix, n1, n2, n3, and n4. And in 2D, please remember that dni over dx is not equal to d zeta over dx times by dny over d zeta, because x equal to a function of not only zeta but also eta. So therefore, we need to use the derivatives by zeta and eta together to form the Jacobian matrix. And we submit all of them to calculate the compacted matrix B dash. After get the matrix B dash, we can pass it back to the full matrix B. So the thing we don't know over here is only the Jacobian matrix. The Jacobian matrix is actually the derivatives of the coordinates over local coordinate. So therefore, it can be derived by dn over d zeta times by the x vector and dn over d eta by x and y vectors. For example, for x, I have x equal to n times by the vector x, where vector x is x1, x2, x3, x4, and therefore we can know what is the derivative of n over zeta because we know the function n1, n2, n3, n4, and we know x1, x2, x3, x4, so therefore we can calculate the x position. It is a reminder, the fifth conclusion, that there are some situations that the finite element method become unstable. For example, in these situations, when we have the triangle one, so it's unstable under compression and shear. And this sliver is also unstable because now we can have some position with the given zeta and eta. The point is outside the element. The matrix of stiffness in 1D is just only the Young modulus value, which is E, and in 2D it is a linear elasticity matrix, which is E over 1 minus nu square, when nu is a Poisson ratio, and times by the matrix 1v v1 and 1 minus v over 2. And the nodal force equal to the matrix K of stiffness times by U, which is the displacement vector. And from the energy approach in the next slide, we know that the matrix K will equal to the integral over the area or volume of the matrix B transpose times by the matrix D times by matrix B again. Please note that in 1D, the integral over volume just is the integral over distance. In 2D, the volumetric integral equal to the double integral over x and y directions and so on. The energy approach is an extra content of this module, so therefore I will not go into detail. Just we compare the strain energy and the work done by the force and find out the way to calculate the matrix of stiffness. The last concept in this lecture is about the Gaussian quadrature. So instead of calculating an exact integral, we may calculate the sum of the functions at some points in the area, and Gaussians propose 4 internal points which may provide a better accuracies at the coordinate of plus minus 1 over square root of 3. So recap, in this lecture we have studied the shape function and the stable conditions and the elasticity matrix by Gaussian quadrature. The coming tutorial, we are going to study how to make a 2D application by programming and by using the commercial software. Thank you very much for your time and see you next lecture.